Hey everyone, and welcome to The Explainer. This session is proudly brought to you by Forge College. Today, we've got a fantastic and honestly, absolutely crucial goal. We're going to take your abstract capstone requirements and translate them into strict, deterministic byte layouts using Borsh. If you've ever found yourself wondering how your high-level product ideas actually live on the Solana blockchain as raw zeros and ones, well, you are in the exact right place. So let's get right to it. Okay, right off the bat, I want you to burn this rule into your brain. Always, always treat incoming bytes as untrusted, mysterious packages. I mean, imagine someone handing you a tiny cardboard box and saying, hey, there's 3 million items in here. Can you go ahead and build a warehouse for them? If you blindly rent out that space based on some malicious length prefix they gave you, your program doesn't just fail, it dramatically crashes and burns. So today, we're setting up the fundamental physics of Solana. We're going to budget every single byte to protect our programs from those tiny exploding boxes.
Now, if you were with us for the last lesson, the capstone overview and project scope, you know we made some pretty massive high-level product choices. You mapped out the domain, the features, the whole shebang of what your smart contract is supposed to do. Now, it's time to bridge that gap. We are officially turning those big product choices into concrete Rust structs. We're taking the theoretical and making it strictly mathematical.
All right, so here is our engineering blueprint for today. We'll cover the blueprint, the physics of sizing, a marketplace prototype, our 5-step formula, and finally, validation and upgrades.
Starting us off with Section 1, the blueprint for Borsh data.
So why are we setting up all these strict structural rules before we even touch the application logic? Well, simply put, preventing utter chaos right now is way cheaper than fixing on-chain bugs later. Our tool of choice here is Borsh. Borsh is a deterministic binary serializer. It writes your typed data into bytes. But, and this is a big but, it doesn't include a self-describing schema. You know how JSON helpfully labels a string as name? Yeah, Borsh doesn't do that. It just hands you raw zeros and ones. And because it lacks that built-in map, the exact order and types of your fields become a rigid, unforgiving sequence. You shift just one byte, and the whole thing completely breaks. Which leads us to Section 2, the physics of Borsh sizing.
Since Borsh isn't going to hold our hands here, we literally have to do a bit of math to understand its binary footprint. The fundamental divide in these Borsh physics is between fixed length types and variable length types. Fixed with primitives like a U64 integer or a simple boolean, those are easy. We know exactly how much space they take every single time. But variable length types like a string or a vector are a lot trickier. Borsh handles these by prepending a critical 4-byte little-endian links prefix. Think of it like a mandatory tiny luggage tag that tells the program exactly how many items are packed inside. Let's actually run through exactly what those encoding costs look like. A U64 integer is exactly 8 bytes. A boolean is just 1 byte. But pay close attention to strings and vectors. They always cost that 4-byte prefix overhead, plus whatever the size of the actual contents happens to be. Even an option carries a tax. It requires a 1-byte discriminant, basically a 0 or a 1, just to declare if the data is actually there, followed by the data itself. Every single byte demands a budget.
Moving right along to Section 3, prototyping a marketplace schema.
So what does this all mean in the real world? Let's take all that abstract theory and anchor it directly to our marketplace capstone project. Imagine you're the engineer tasked with budgeting the actual on-chain bytes for this app. We're going to need a persistent marketplace config account to store our global settings, and mutable listing accounts for the individual items. How do we actually go about building these structs? Let's tackle the global configuration first. For our marketplace config v1, we have a 1-byte version tag, a 32-byte pub key for the owner, a 2-byte integer for fees, and a 4-byte integer for maximum listings. But notice that last field there, a reserved vector. Guys, this is an incredibly smart engineering practice. It's essentially our safety hatch. We're intentionally budgeting extra empty space so that if we ever need to add new features later on, we already have prepaid room to grow without completely breaking the account structure. So when we build this out, we need exactly 171 bytes, period. How'd we get that? Well, it's 39 bytes for our fixed fields, plus that 4-byte prefix for our reserved vector, plus 128 bytes we've decided to allocate as our reserved safety space. Add it all up, and we allocate 171 bytes at deployment. There's no guessing involved here, just cold, hard math. Now let's look at the mutable listing account. This one is a bit trickier because it has text fields, a title, and a description, which means variable lengths. But remember, we absolutely cannot have unbounded data on Solana. We have to calculate the worst-case maximums. If we restrict the title to 64 bytes and the description to 512 bytes, and then add in our 4-byte prefixes and all our fixed identifier fields, we hit roughly 689 bytes. And in practice, you'd round up and add a nice safety margin to this number just to be sure.
Which brings us to Section 4, the 5-step design workflow. Now that we've prototyped it, let's turn this into a repeatable system you can actually take to your own code bases. Step 1, extract the structural requirements right from your product specs. Step 2, explicitly choose between fixed types and variable length types using strict maximums. Step 3, always add a version tag and reserved safety space. Step 4, compute the exact byte capacity for your deployment scripts. And finally, Step 5, define strict validation rules for when you read the data back out. Doing this systematically translates squishy product ideas into reviewable mathematical schema designs.
But wait, what happens if you genuinely have unbounded growth? Think of it like a hoarder trying to cram their entire, ever-growing lifetime collection into a tiny studio apartment. It simply won't work. Never ever embed an ever-growing vector in a single account. Instead, you want to split that data across separate program-derived accounts, or PDAs. Just create a new, discrete account for each new item. Trust me, boundedness is your absolute best friend here.
And finally, Section 5, validation and safe upgrades.
Knowing how to pack your data tightly into bytes is honestly only half the battle. The other half? Reading them safely. When you're deserializing, essentially opening those mysterious packages we talked about earlier, you absolutely must run runtime assertions. Verify that the length prefixes don't exceed your planned maxima. Confirm your numeric ranges actually make sense. Check your logical invariants, and for goodness sake, validate those signer pub keys. If an account fails these checks, return a controlled error. It is infinitely better to gracefully reject a transaction than to let your program panic and completely soil itself on-chain.
And guys, here is the absolute golden rule for schema evolution. You have got to embed a U8 version field at the very start of every serialized state. It has to be the absolute earliest serialized byte. Why? Because years from now, when you've upgraded to version 3 of your program, your older code or clients need to be able to read that very first byte, instantly recognize an unsupported version, and safely step away before misparsing the rest of the data. It's a lifesaver.
So there you have it. You've got the blueprint, you understand the physics, the workflow, and the golden rules for validation. In our very next lesson, we're going to take these exact blueprint schemas and convert them into live, breathing Rust code using the BorshSerialize derives. It is going to be incredibly satisfying to see all this math actually turn into logic. Before we wrap up, I want to leave you with this provocative thought to chew on as you look at your own projects. Are your on-chain bytes strictly bounded right now, or are you just kind of guessing their size? Well, that's all for today. I want to thank you so much for joining me. Remember, this explainer was proudly made by Forge College. Be sure to head over to forge.college to learn a whole lot more about this subject and tons of other fascinating Web3 topics. I'll see you next time.